So we have talked about a DFA framework and its properties that need to be true for the fixed point iteration algorithm to converge. So given a data flow framework which is specified with f, v and the meet operator, which is monotone, and the semi-lattice formed by v and the meet operator has finite height, then the fixed point iteration is guaranteed to converge. So we have been stating this result or this theorem, but today we are going to discuss this in more detail and also share a proof sketch for this particular theorem. Okay, and moreover we say that it's not just true that it converges, but if we initialize all the interior points to top, so all the interior points are points that are not part of the boundary condition, then the algorithm yields the maximum fixed point solution of the DFA equations. So I'm using this term maximum fixed point solution of the DFA equations. Recall that data flow analysis is basically specified as a system of equations. We are interested in finding a solution that satisfies that system of equations, and the fixed point algorithm is one way of identifying such a solution. And we are not just interested in any solution, we are interested in the most precise solution. And one way to say that is that we are interested in the maximum such solution, where maximum is defined with respect to the ordering operator less than equal to of the semi-lattice. In other words, we are interested in the maximum fixed point. So what is a maximum fixed point? Let's try to understand that in a little bit more detail. Recall that any solution will have a value associated with each program point. So for example, the value at the loop head is going to be something, the value at the loop tail is going to be something, and at every basic block in the beginning and the end there will be some value. An MFP solution, the maximum fixed point solution, or MFP solution, has the maximum value at each program point such that these values satisfy the equations. So if I look at all the possible solutions that satisfy these equations, there will be one solution where all the values are maximum across at all the program points compared to all the other solutions, and you know we can argue that such a solution will exist, and that solution is called the maximum fixed point solution. All right, and where maximum here is based on the less than equal to operator of the semi-lattice. Alright, so let's look at an example to understand MFP in more detail. So let's look at the constant propagation example, and once again the lattice is formed by top, constant value which could be anything, and bottom. And then let's look at this particular program. Let's say I initialize x to 3 and then I say y equals z plus w, some random stuff, and then there's a loop here. Now this solution here, which is associating empty set at the beginning of the program, x equals 3 at and all the other points of this program, is the MFP solution I claim. Here is another solution that would also satisfy the data flow equations, and that solution is basically giving me x equals 3 at this particular point, but it's giving me the empty set at all the other locations. Now I'm claiming that both these solutions are satisfying the data flow equations. So maybe we want to check, and so we can see that across in and out, this is phi and this is x equals 3, and if I use the gen and kill form of constant propagation transfer functions, then the value at the end of this trans statement includes this extra generated mapping from x to 3, and that's true for both the solutions. Now let's look at this particular point at the loop head. Here it needs to be the meet of the values coming from the initialization x equals 3 and the loop tail. And in the first case, the loop tail is x equals 3, so the loop head is still x equals 3, so everything is good. And so the first solution satisfies the equations. Let's look at the second solution, which is empty set and empty set. So the first, at the loop head, I say that it should be a meet of x equals 3 and the loop tail value, which is the empty set. So what is the meet of empty set with x equals 3? It's the empty set. And so even the second solution actually satisfies the data flow equation. So both these solutions actually satisfy the data flow equations, but the first solution is the maximum such solution, and that's why it's called the MFP. The second solution is a fixed point because it satisfies all the equations. So it's we just call it the FP solution, but not the MFP solution. It's a fixed point solution, but not MFP. All right. So now what is the explanation? What is the explanation that the fixed point iteration algorithm is guaranteed to converge? So here is the rough explanation. That value at any program point can only decrease because meet operator just decreases that value. So if there's some value somewhere, then it can only go down and from there. And because we start with all the unknown values at the interior points with top, we should hopefully get to the maximum fixed point because we are decreasing only by the amount that is required. All right, we're going to discuss this in more detail very soon. So why are values only decreasing? Because when we meet, we are only assuming that the original the incoming values have decreased, the meet value will also decrease. And because of monotonicity, if the value at the beginning of a basic block for a forward DFA has decreased, then the value at the end of the basic block will also decrease, and that's coming from the monotonicity property of the transfer function. And so these properties will provide convergence, and we're going to discuss this in a little bit more detail. The other question is, how do we say that this is the MFP? And so for that, we basically use this argument that values do not come down unless some constraints from the equations drive them down. All right, and so the values are brought down by the minimum possible amount such that they start satisfying the constraints. And that is our rough argument for the maximum fixed point solution. Why is it maximum? Okay, so let's try to prove this, and I'm going to show you a proof sketch based on induction. And so first we want to prove that the values at the k+1th iteration of the fixed point solution are no greater than the values at the kth iteration. By no greater, I mean they're less than or equal to. So the values at the k+1th iteration are less than or equal to the values at the kth iteration. This is what we want to prove, and I'm going to use mathematical induction to try and prove this. So here's the base case. The base case, we want to prove that the values after the first iteration are no greater than the initial values. Now this is easy because the initial values are just the top value, and so this is trivial actually because all initial non-boundary values are top and all the boundary values are anyways fixed. So anything, any other set of values will always be less than equal to the initial values because that's how we are initializing it. So our base case is trivial, and that's just coming from our initial values which are set to top for all interior points. Now here is our induction hypothesis and induction step for mathematical induction. So induction hypothesis, let's assume that after the kth iteration, the values are no greater than those after the k-1th iteration. So if the values at kth iteration are less than equal to the values at k-1th iteration, then we want to prove that the values at k+1th iteration are also less than equal to the values at the kth iteration. In other words, if this is the k-1 values, and if I am able to say that vk-1 is less than equal, I want to say, let's say I've been able to say that vk is less than equal to vk-1, and this forms our induction hypothesis, right? So this forms our induction hypothesis. And what is our induction step? Our induction step is vk+1 is less than equal to vk. So assuming the induction hypothesis, we are interested in proving the induction step. Okay, so how are we going to do this? So let's assume forward DFA for this discussion. We could have done the same thing with the backward DFA without loss of generality. So in the forward DFA, we have this, let's say we have some basic block and we have multiple incoming predecessors, and the value being computed is at the beginning of this basic block that's called in of S, right? Where S stands for some statement or basic block. And then we say that in of S equals meet over out of P, where P belongs to the set of predecessors of S. So we we meet the out values of all the predecessors to obtain in S. Now we know this data flow equation, and in our fixed point iteration, what do? We basically keep iterating. So at the ith iteration, we take the values at the out values of the i-1th iteration to arrive at the values of the in values of the ith iteration. So to capture that, let in s superscript I and out s I denote the values of ns and out s after the ith iteration for any s, including p and everything else, right? So let ns I and out s I denote the values of ns and out s after the ith iteration, just after the ith iteration. Then we can write this particular equation as the following: in s, k plus 1 equals meet of out of p of k. So the values at the end of the kth iteration are met with each other to produce the value of in s at the k plus 1th iteration. Now, you may say, oh, why can't I just update? So I'm assuming here that, at one step, we're just taking an original snapshot and using that to get the next snapshot in our fixed point iteration algorithm. Of course, when we use the worklist algorithm and things like that, we need to have more nuanced arguments on why this is true. But let's just take the simple algorithm where we just in one snapshot we just propagate the old values into and meet them into the new value. And so this is what our algorithm is going to look like in that case. Now from here we can show that n of s k plus 1 is going to be less than equal to n of s of k. So how? I'm going to use mathematical induction. We know that out of p of k is less than equal to out of p at k minus 1, and this is coming from our induction hypothesis, because we said that values at iteration k are less than equal to the values at iteration k minus 1. So that also means that the out value at any predecessor p at the iteration number k is also less than equal to the same value at the iteration k minus 1. Thus, if I meet over all the out p, meet over all the p's for out p at iteration k, that's going to be less than equal to meet over all the p's at iteration k minus 1 or for out p. And notice that this is just n of s k plus 1 and this is just n of s k, and so from there we get n of s k plus 1 is less than equal to n of s k. So we have been able to use the induction hypothesis to show that the in values for any basic block at the k plus 1 iteration will always be less than equal to the in values of the same basic block at the kth iteration. Now we need to show the same thing for the out values, right? So that's the only remaining part of the proof, and that's also easy. Notice that out of s k plus 1 is nothing but transfer function applied to n of s k plus 1. And we know that n of s k plus 1 is less than equal to n of s k. We just proved it on the previous slide. So from the monotonicity property of the transfer function, we know that because n of s k plus 1 is less than equal to n of s k, we know that out s k plus 1 should also be less than equal to out of s k, because fs is monotonic. It maps smaller inputs to smaller outputs. Okay, so that's our proof sketch, and based on that we have been able to show that the values in the data flow analysis can only decrease, assuming that the framework is monotonic, and all right. Now assume if the values can only decrease, then if the semilattice has finite height, then after all at some point they will stop decreasing, because in the worst case all the values are going to reach the minimum value, which is the bottom value. And so from that we basically can prove that the algorithm will definitely converge or terminate. Hence we have been able to prove that that the algorithm terminates. Now the second part of the claim which we want to prove is that the iterative algorithm yields the maximum fixed point. Now it converges, all right, but what is the proof that it yields the maximum fixed point? Now there are two parts to this. First of all, we need to show that it actually yields a fixed point, and that will be easy to show because after all we only stop when all the equations are satisfied. That means it is a fixed point. And the other part is that it is the maximum such fixed point, all right? And so here is the proof sketch. The algorithm terminates only if all the equations are satisfied, and that basically tells us that whatever solution we get at the end of the algorithm, when the algorithm has actually terminated, it has to be a fixed point, because that's the only condition under which the algorithm terminates. And second, if an equation is not satisfied at any step, the value is driven down by only that amount so that the equation now becomes satisfied. So we basically take the smallest possible step so that the equation becomes satisfied, and so from that we know that we are going to stop only when only after we have, so we would have taken the smallest amount of number of steps and amount of step, gone down in the solution by the smallest amount at every step, and so even in the whole we would have gotten down by the smallest amount. And so that's the argument for the maximum fixed point. Now this is just a proof sketch. More formal proof will also have more formal details and sketch, but that's basically than the sketch, but that's beyond the scope of our discussion.